Hello students. So this is lecture number 28. We will be continuing our discussion on differential amplifiers, and we will start our discussion, or rather have a very brief discussion on tuned amplifiers. Now in the last class we saw how a differential pair works. We took the example of a BJT, right? We put two common emitter amplifiers together and we assumed that these two transistors, let's say Q1 and Q2, are identical, and this was our V in plus and this was our V in minus, right? And we said that we're going to bias this with a current source. Now this can be called as I tail or whatever, so let's stick to our convention, I tail. And so you have two separate outputs. Let's call it as our Vout1 and Vout2, and so I think we had decided which was Vout1 and Vout2. Basically, just to reiterate, so if there is a delta V by 2 plus delta V by 2 on the VNP and minus delta V by 2 on the minus side, so the current that is going to flow here is Gm delta V by 2, and this is minus Gm delta V by 2, right? So because of this, delta V out 1, rather actually this is supposed to be 1, right, is basically equal to minus Gm delta V by 2 into R, and delta V out 2 was plus Gm delta V R by 2. This is because as more current flows, there is more drop across the resistor, and therefore V out 1 goes low. On the other hand, there is a lesser current, so the overall current I1, okay, let's say the total current I1 can be written as what? I tail divided by 2 plus Gm delta V by 2, right? And the total current I2 can be written as I tail by 2 minus Gm delta V by 2. And therefore, the actual V out 1 can be written as VCC minus I1, let's say this is VCC, I1 times R, and V out 2 can be written as VCC minus I2 times R, from which we basically get this result. Delta V out 1 and delta V out 2 happen to be in this way. Okay. So if you say, so which of the output ports correspond to which input port? In other words, how do we write the polarity? So if we say that our op-amp, now this is a fully differential op-amp, or okay, let's not call it an op-amp at this stage, but typically you will see that this is the first stage in any op-amp that you would see. Okay, this is a fully differential one, so if this is plus and this is minus, right? This is V in plus, V in minus. The output terminal which has the same polarity is what? V out 2. Okay, so this is V out 2 becomes the plus terminal, and the minus terminal is V out 1. Okay, so when this voltage increases, this V out 2 increases, right? And as this V in M decreases, V out 1 decreases. Okay, and vice versa. Okay, so this is how we establish the polarities. Now let us go a little deeper into this circuit. Okay, so one thing is this particular node P, right? The node P where the tail current source is connected. This node we mentioned is basically it does not respond to differential signals. The way to understand it is that, so let's write it like this, right? So when you have this, let's say this is V in P, this is V in M, right? Right. Now V in P becomes, let's say, the common mode DC voltage plus some delta V by 2, and V in minus is basically common mode DC voltage minus delta V by 2, right? This is how we have assumed our inputs to be, right? Now what happens is VBE1 becomes your VBE DC Okay, that is like when there is no differential signal, or basically when there is no AC signal riding on top of your input, right? VBE DC plus delta V by 2, and then VBE 2 basically becomes the same VBE DC minus delta V by 2, which is why you have the differential currents getting set up. And therefore, if you look at this node VP, right, the node VP basically is nothing but the average of VCM DC minus VBE DC. Okay. This is the node voltage at P, and it does not change. Okay. Of course, the caveat is that this is applicable only for small signals, right? For small differential signals. Okay. Now, how to analyze? Of course, we have written. I think in the last class we wrote down the gain expression. But for any arbitrary differential circuit, so this is a very elementary differential pair. Okay, this is what is called as a differential pair, or a small differential amplifier. Now, the way that you analyze this circuit is like is by doing is by constructing half circuits. Okay, we'll see the concept of half circuits. So, what is the concept of half circuit? So, this is our actual circuit, right? And we have mentioned time and again that this is a highly symmetrical circuit, right? Q1 and Q2 are exactly identical, and both the resistors are exactly the same. So which means that in order to do our analysis, it is very useful for us to kind of dissect this circuit in the middle. Okay, and we form, first let's form what is called as the differential half circuit. Okay, what do we mean by differential half circuit? How does this circuit respond when it is given some differential signals? Okay, so the definition of differential signals and common mode signals and all that we have already seen in the previous class, right? So if you have, let's say, V in 1 and V in 2, right, the differential mode signals is nothing but V in 1 minus V in 2, right? And the common mode signal is basically V in 1 plus V in 2 divided by 2, right? And basically what happens is you have VDM by 2 plus VDM by 2 here, and minus VDM by 2 on the other side, right? So this is how we split the circuit, split the signals. Now, if you form a half circuit, right? This is VCC. You have an R. You have this transistor, right? This is your VN. This circuit is applicable only for differential signals, and we saw that this node P does not respond to any differential signals. So this can be called as a virtual ground. Okay. So the differential mode half circuit is basically what? A common emitter amplifier. And the differential mode gain that you get here is what? Minus GM times R. Alright. So this basically is the same what we derived in the previous class, that we set up all the voltages and currents and we calculated the gain to be the pretty much same thing. Right? Now you can also look at the common mode half circuit. Now before we go into the common mode half circuit, in practice any current source is basically going to have a shunt resistance. Let's call it RT. Okay, so that is going to be there in any current source, right? And in most cases this current source is formed by means of using either the current source, let me just put it here, or let me do it in the next. So the current source implementation, you'll basically see two types. One is to use a simple resistor. Okay, of course this has its own disadvantages. If you wanted to, what happens when you just put a resistor here? Tail. I mean, this can be a dual supply also, plus VCC and minus VEE. Now what happens is basically that if you look at this circuit, right, the common mode part of it, right, if the common mode signal increases on both sides, this node P will also increase. Okay, notice it does not, it react only for differential signals. For common mode signals, it will react. Okay, now automatically this is that negative feedback action that we have been talking about for quite some time, right? And so this emitter resistor is going to kind of control the current and keep the current, the I tail which is flowing here, to be fairly constant. Okay, so it's a kind of a poor man's current source in this context, right? Now the other way to do it is basically to use a BJT in forward active mode, right? So you can basically put a, you can bias it properly. You can bias it, the way to bias it we have already looked at. You can use a current mirror, right? So you push a current into a, into an existing another BJT and diode connected, and that way you will be able to mirror the current and form this current source. Now what is the R out of this current source? This is nothing but the R naught of the BJT. Okay, so either way you have some resistance. Now when you form the common mode half circuit, what do you do? Okay, so basically you have the R here, okay, and then you have the transistor here, right? And on top of the on top of it, this node P is no longer a virtual ground, and therefore you have to kind of split this resistor also, right? You're basically going to split it in half. So how can you split this resistor? You can split this resistor by saying there is some R tail here. Okay, so the R tail can be an explicit R tail or it can be the R naught. But how do you put it? Because it is a half circuit, you put it as 2 times R tail, right? So that when you join both circuits together, you get back the original circuit. Okay, you take two half circuits, kind of join them together, you should basically get back your original circuit, right? So in that case, you need to use 2 times R tail, right? So this is how your, so this is your common mode half circuit. Okay. Now as I mentioned, common mode signal has a common mode DC component, plus it can also have a common mode AC component. Now in our discussion last class, this common mode AC component can be the interference from, let's say, power supply lines, power lines, or RFI, or any other kind of interference. Okay, so this is your time varying common mode signal, which is the common mode noise which we defined earlier, which you want to get rid of. Okay, so when you have a common mode noise, of course you need this common mode DC to bias the whole thing, right? Without that, the whole circuit is not going to work. Okay, unless you get a, unless you put a dual supply voltage, right? In that case, of course, it will still work, but again, the common mode DC is going to be 0 or something close to 0. Okay, so what we are looking at in this circuit is the behavior of the circuit to common mode AC signals, okay, or common mode AC small signals. Now, how will this behave? Basically, what is this circuit? This circuit is nothing but a common emitter with a emitter degeneration. Common emitter with emitter degeneration, right? And what is the common mode gain that you can talk about, right? The common mode gain can be given as Gm times R divided by 1 plus Gm into the resistance at the emitter, which is 2 times R tail, right? This is your common mode gain. Okay. So your differential, we have found your differential mode gain here, right? And we found the common mode gain, right? And the ratio between the two is what is defined as CMRR. So I think you have already studied about common mode rejection ratio in Dr. Anup's part. So I'll just write the expression here, ADM by ACM. Okay, so what do you get? GMR divided by, so if you take the polarities appropriately, you can drop the negative sign. You get GMR divided by 1 plus 2GM RT, right? So CMRR basically becomes 1 plus 2GM RT. Okay. Now what do we see here? As R tail increases, right, you get better CMRR. Okay. Of course, you cannot keep increasing. If you are going to implement the constant current part of it by just using a resistor, if you keep increasing the value of this R tail here, right, what happens? This node voltage VP also DC voltage keeps going up. Okay, which means that your common mode DC also has to increase correspondingly, and your output DC will also has to be higher, which means that you have limited swing. Okay, so which is why using a transistor as the tail current source is a very effective means of implementing this current source. Okay. Reduced swing if our tail is employed, our tail is used. Okay. Basically, that is why BJT based current source, because what is the minimum voltage that you require across the BJT here? You just need to be above, right? You need, it has to be greater than, VCE should be greater than VCE sat, right? If that condition is satisfied, you are good to go. Okay, and therefore your is better. Okay, and what is the limit on the input common mode voltage? Common mode DC input should be greater than or equal to VCE sat of, let's say, transistor 3, okay, plus the VBE of transistor 1, 2. Right? If this condition is satisfied, the circuit will basically work. Okay, and what is the V out common mode DC, which we have already seen, which is VCC minus IC times R. Okay, so or in other words, IC is nothing but I tail divided by 2 times R. So you have to you need to basically design it in such a way that it is fairly close to mid rail for better performance, better swing performance. Okay, all right. So with this, we complete our discussion on differential mode circuits or differential amplifiers. The op-amp based versions you have already studied in the other part of this course. Okay. Now we will move to another topic, which is tuned amplifiers. Okay. Now we have already studied about RLC circuits, right? And so we will be using some of those concepts here. Now, why do we go for tuned circuits? Okay. Now, the main motivation is, if you take, let's say, a common emitter amplifier. Now, before I kind of go further, let me just make another comment here. Okay, similar discussion holds good for MOSFET also. Okay, so only thing there is, instead of so what will be your common mode DC input? That should be greater than VDS sat of 3, okay, plus the VGS of 1, 2. Okay, VDS sat of 3 is nothing but VGS 3 minus VTS. Okay, so other than this difference, everything else basically holds the same. The same analysis holds good. All the things that we have seen remain to be the same. Okay, all right. Of course, the expression for GM and other things will differ. All right. Okay. Now coming back to our V in, let's say this is a V out. Now usually the capacitance at the output node, okay, can be taken to be some load capacitance. Okay. Now where is this load capacitance coming from? It is also the capacitance uh, C mu capacitance, right? So what is this capacitance? This is the C mu of Q1. Let's say this is Q1 plus the input capacitance of the next stage. Okay. So this amplifier is going to connect to some other amplifier, so which will have some capacitance at the input plus some resistance also, of course. But we have already seen for higher frequencies like how the capacitance starts dominating. So the CBE or the C pi plus the C mu multiplied by the Miller capacitance will be the input capacitance of any common emitter amplifier. So that, the effective capacitance will also be there. Okay. Now, what do we know from this? Basically, because there is a capacitor here, we are going to have poles, right? And if you say that the pole due to poles are present, which basically means what? You have a low pass response. Okay. If the pole due to CL is the dominant pole, so what do we mean by the dominant pole? Basically, that is the lowest pole, right? Lowest pole, because that is going to dominate the response of your entire circuit, right? Now, then what happens is bandwidth is pretty much equal to the dominant pole. Okay, let me call it omega PD. Right? This is your 3 dB bandwidth. Okay. Now, suppose, for example, okay, suppose the 3 dB bandwidth. What was it that you had, seen in your lab class? Probably you would have had around 1 or 2 megahertz, right? Right? 1, 2, 3 megahertz. That's kind of the range in which you would have seen the bandwidth to be, right? Of course, when you are measuring things in the lab, right, the input capacitance of your oscilloscope also comes into the picture. The oscilloscope's input will have some 10 mega ohm or some resistance in shunt with some, if I remember right, it will be some 11 picofarad or something like that. I don't know, these oscilloscopes in our lab, I'm not sure, but certain other oscilloscopes, I remember the values to be something around this. Okay. And those are supposed to be high bandwidth oscilloscopes than what we have in this particular lab. Okay. So whatever it is, you get a bandwidth which is something like this. Okay. Now, for example, suppose if you want the circuit to work at, let's say, uh, 20 megahertz, just for example, okay? 20 megahertz. All right. Now, what can you do? You can't do anything. Only thing that you can do is to keep the solution is, it's not a good solution. Let's say a bad solution is to reduce R. Okay. So if you reduce R, what happens? 1 by 2 pi R times CL will basically go up, and the gain GM times R will also go down. Okay. And then V out DC will also basically go down. Right? Sorry, go up. It will go up. Right? Now, this is a bad solution. Now, what is the other way to get it to work? For example, suppose this, instead of 20 megahertz, I wanted to work at, let's say, 50 megahertz or even beyond. Okay, how much can you reduce R? Okay, CL you can't do anything because the BJT has certain capacitance. Let's say you're driving an oscilloscope or you're driving some other circuit whose input capacitance also cannot be changed. Okay. So the way in which you can make this work is to use the good solution, to use resonant networks. Okay. So what we are saying is basically, let's bring in our inductor. Okay. Now this is your V in. Let's say there is this capacitance. Of course, usually along with the capacitance, you will also have some RL. for example, if it is driving another BJT, it will have a certain input impedance, right? We have already derived the input impedance, and it has, in fact, for most of our analysis, we have looked at the input impedance. It was a real part. It was a resistive impedance, right? Of course, the capacitance comes into the picture only at the higher frequencies, right? Now, on top of that, this inductor also is a lossy inductor, right? And if you recall our the stuff that we talked about in the network analysis class, we saw that a lossy inductor can be represented as a L with a series R, and this can be transformed into a L with a shunt R, right? We looked at the transformation and the way in which you can do this transformations and so on. And based on this, we defined what was called as the Q of the inductor, right? It's not Q of this resonant network. It is just the Q of the inductor. The Q of the inductor will give you either RS, or you can also look at RP, right? So Q is equal to omega L by RS, right? Or the Q is also equal to RP by omega L, okay? And this Q is defined at a particular frequency, or rather at different frequencies you define the Q values, and then at different frequencies you'll be able to get the loss. Like if you do a little more on electromagnetics course, you will know that any inductor will have some eddy current losses and things like that, and the skin effect will also be there, right? And the skin effect is a frequency dependent effect. So the skin effect loss will be a frequency dependent loss, okay? So that is why Q becomes frequency dependent, okay? So so all that apart, so we know that at a given frequency, let's say now we are interested in 20 megahertz, we are bringing in an inductor, and that inductor has some shunt resistance, which can be modeled as, let's say, some RP here, okay? Now, if you draw the small signal equivalent circuit, right? So what do you get? You have basically R pi here, and let's also put C pi, okay? C pi plus AV plus 1 times C mu, right? And you basically have GM times VGS, right? Where VGS is defined as the voltage across this, sorry, not VGS, VBE, right? So this is VBE, right? And what else do we have? We have R naught, and then we have, of course, C mu into 1, right? We have used the Miller equivalent. I mean, we have used Miller effect to kind of bring out this capacitance. And then what else do we have? This is our output node, right? This is a collector node. You basically have RP and you have RL, right? And then you also have the inductor going to ground. And not only you have the inductor, you also have CL, right? Right. So this is our intrinsic. This particular part is our intrinsic device, right? Where we have included C pi and C mu, right? And then this RP is because of L, RL is at the output, CL is at the output. Okay. Now you can reduce this whole thing into what? You can say, okay, there is R pi, let's say C pi plus AV times 1 C mu. You have your GM VBE. Okay. I'm going to say that here, basically you're going to have some R equivalent, some C equivalent, and a L. Okay. Right? Now, what is R equivalent? We can write R equivalent to be nothing but R naught parallel to RP parallel to RL, and C equivalent can be written as what? C mu plus CL. Okay. Now, what do we end up here with? We basically have a RLC network, right? So if you consider, or if the case is such that the load capacitance is much higher then C pi and C mu and so on. Okay, you can say that pretty much like if this pole, let's say this is omega p2, this omega p2, if it is much greater than the resonant frequency here, right, or much lower, whatever, I mean, or much greater than that, then what happens? The response is pretty much dominated by this resonant network at the output, right? So, for example, if I just want to give a small example, if I say that this R pi and this C pi C mu combination is basically going to be at, let's say, some 100 megahertz, and whereas we are interested in 20 megahertz, okay. So your R is equivalent, C equivalent. Basically, the way in which you design the L is such that this resonant network on the right hand side is going to resonate at the frequency of interest. So how do you design that? So omega naught is equal to 1 by root of LC, right? L into C equivalent. So this is the way you design L, right? And then what happens? You also, this is a parallel RLC network. Okay. So if you consider omega naught to be, smaller than, let's say, omega p2, okay. In other words, you can neglect the effect of, let's say, C pi plus C mu times 1 plus AV into R pi. Now what happens? Your V out by Vn of S is given by what? Gm times Gm Vn, right? Divided by the parallel combination of this into the impedance given by R into basically, or divided by the admittance. What is the admittance? 1 by R plus 1 by SL plus SC, right? This is your admittance, right? Now this is the combined admittance. So if you solve this, basically what you would get is basically Gm by C. So let's try to solve this one, right? So what will you get here? SL plus R plus SLRC, okay, and you get SLR into Gm, correct? Or rather, sorry, S squared LCR. So let us divide the whole thing by R. What will you get? You will basically get SL divided by SL by R plus 1 plus S squared LC. Okay. Now you can also divide this whole thing by omega naught squared, right? So basically you will get 1 by S by C divided by S divided by, you have RC plus 1 plus S squared, right? So basically this is into Gm, of course. So this is nothing but what we have already seen, right? No, 1 by LC, right? So this is nothing, 1 by RC is nothing but 2 times Q, right? So so basically we can define, so this becomes a second order network, right? V out by V in of S becomes S by C times Gm divided by S squared, okay? Basically you want S squared to be, yeah, S squared plus S by RC plus omega naught squared, okay? And what is S by RC? 1 by 2 RC is alpha. So you can write this as S by C Gm S squared plus 2 alpha S plus omega naught squared, right? Of course, we can, from alpha we can write Q. So basically you can define the Q, right? What is the Q? Q is 1 by omega naught RC, right? Or it is basically R divided by omega naught L, right? So this Q will basically give you the bandwidth, right? So what is the bandwidth? So this is a tuned response, right? Now we have already seen the response of this circuit. So at DC, okay, the gain is 0, okay? And the gain at omega naught, what happens to the gain? Gain is basically given by, so what happens to this parallel network? You only have R equivalent. So GM times R equivalent becomes the, or let's say the magnitude of the gain, right, is equal to GM times R equivalent. Okay. And at omega tending to infinity, again the gain tends to 0. Right. So if you want to plot the gain, right, let's say this is your omega naught, how will this gain basically be? So it starts as 0, right, and it's going to peak at a certain point, which is nothing but omega naught, and then it is going to kind of go down like this. And the peak gain, right, magnitude of AV is nothing but GMR at the resonant frequency, and at other point it is going to go down, right? So if you design this resonant network, like we started off with the example where we wanted this amplifier to work at 20 megahertz, if you design the L in such a way that it resonates out the capacitance at that frequency, you will basically get an amplifier which is working at 20 megahertz without you doing, without you losing all the other benefits, right? You get the same gain of GMR equivalent, right? While at the other frequencies where you are not interested at, you don't get the gain. So basically, this is what is called as a tuned amplifier. Okay. Now we have already discussed about bandwidth and Q, right? So how is Q and bandwidth related? Bandwidth is given by omega naught divided by Q, right? So if Q is high, what will happen? The bandwidth is low, right? And if Q is low, then the bandwidth becomes high. Okay? And we have already looked at the expressions for Q. So you can basically design, not only design this tuned amplifier, so you can design for the center frequency. You can basically design for bandwidth or Q, and at the same time you can design for max gain, right? Of course, not all three can be satisfied at any given point of time, right? But you can basically have your approach in such a way that all these points can be covered. Okay, because here these 2 points you will have some trade-off, right? So if you want a higher max gain or higher resonant gain, then you will have to kind of sacrifice on Q, and vice versa. Okay, all right. So this is our this is how we design tuned circuits, right? And we have already looked at what is defined as bandwidth is basically the minus 3 dB bandwidth and all those things. All the discussions that we had for the resonant networks in the network analysis class are applicable here, and they need to be applied here. Okay. So in closing, let me just talk about multi-tuned networks. Multi-tuned amplifiers. Okay. In the previous example, I mentioned that the input capacitance, I mean, you just assume that CL is large enough, so, and your resonant frequency is smaller than your omega P2, right? And many cases, in some cases it might work, in some cases it may not be good enough. So what you need to do, you need to tune the input, or rather let me just say tune out the input capacitance and also tune out the load capacitance. Okay. What do I mean by tune out? Basically put an inductor such that it is going to take care of your capacitor. I mean, you make it a resonant network. Okay. So basically what does that mean? So if you have something like this is CL and this is, let's say, RL, this is your V out. Let's say you have some, because for the sake of biasing, you will have some RE, so shunted out by CE. Anyway, at high frequencies, this doesn't really byte is. Here again, if you want, you can have a DC block capacitance. If not, you can leave it. Okay. So what you can have is you can have a, instead of just having a resistive divider, you can basically have some RF choke with resistive dividers. Okay. And or maybe only on one side you can have an RF choke with the resistor RF choke. Okay, with the resistive divider R1 and R2. Okay, you can have choke on both sides as well. So, all right. So what this will do is, of course, again here you can put a capacitor. Of course, the larger the capacitor, the better it becomes. The short becomes even more effective. Okay. So now what happens is, let's say this is RFC and this is L1. Okay, or in other words, you can also say that this is L2, some other value of inductor. Okay. Now what you do is basically you are tuning out the input capacitance by L2, and this is done by L1. The load capacitance tuning is done by L1. Now, as we have already seen in the case of multi-stage amplifiers, right? So what happens to the in the case of multi-stage amplifiers, when you have multiple amplifiers with poles cascaded, right? What happens? The effective bandwidth reduces, correct? So, but that is for a low pass case. Now, what do you have? You have two RLC networks here, right? Both are in cascade. So basically, what will you have? You will have some A divided by S squared plus 2 alpha 1 S plus omega naught squared into another B S squared plus, let's say, 2 alpha 2 S plus omega naught squared. Now you have a fourth order network. Okay, so both are, I mean, you can kind of intuitively understand. So both are simultaneously tuned to omega naught. So what will happen is you will have a reduction in bandwidth. Okay, this is to be expected. Okay, because you have two resonant networks, both tuned at the same frequency, and therefore you will have even more of a sharper response. Okay, it is the multiplication of two transfer functions, and therefore your bandwidth is now going to be even smaller. Okay, now sometimes you can kind of turn the whole plate around. Okay, let's say another scenario that you might encounter. See, in certain cases, certain applications, small bandwidth might be okay. But in certain other cases, you might want to have a bigger bandwidth, right? For example, at 20 megahertz, maybe your 3 dB bandwidth is just about 1 megahertz, which means, around 20 megahertz, there is a 1 megahertz bandwidth. Now, suppose you want some 3 megahertz bandwidth. Okay, what can you do? You can, one option is, okay, this is a scenario. Okay, bandwidth of the tuned amplifier is not sufficient. Okay, now what is the solution? One is to reduce the Q, right? Now if you reduce the Q, again what will happen is the way in which you can reduce the Q is you will have to sacrifice on gain, right? You will have to sacrifice gain, and you may even have to sacrifice selectivity. Okay, there is another way to do it, which is basically what is called as staggered tuning. Now what is staggered tuning? So let me first give you the frequency domain picture so that you will kind of get it in a better way. Let's say I have two tuned networks, right? Two RLC networks. Now I am not going to tune them both at the same frequency. Okay, I am going to tune them at slightly different frequencies, or in other words, slightly different or slightly staggered frequencies. So let me illustrate what that is. Let's say my first network is tuned like this, omega naught 1. Okay. And my second network is going to be tuned slightly away like this, omega naught 2. Now the overall response, okay, is going to look something like this. Okay. Let me say that this is resonant network 1, and this is basically resonant network 2. Okay, and the composite response is given by what I have done is I've kind of flattened the top while kind of retaining the slopes. Okay, I have staggered the tuning. Okay, so that what has happened is that the center frequency here I am getting better 3 dB bandwidth. Let me call it FL and FH. Okay, the 3 dB bandwidth is better than both of the two resonant networks individually, but you have to do it very carefully such that you just slightly staggered it so that you kind of get a more rounded, flattened response around the actual center frequency that you need. Okay, so that you get a wider bandwidth at the center frequency that you need without sacrificing, because you do have a little trade-off with the gain, that is true, but still this is something which is much better and more acceptable. Okay, so this is what is called as staggered tuning. So for example, in the previous case, you can tune the first network to, let's say, this can be done at omega naught 1 and this can be done at omega naught 2. Okay, and the bandwidth can be much better. All right, so you can go through these. This is a short material on these different types of amplifiers, and we can even the material on differential amplifiers, multi-stage amplifiers. Just go through them in the textbook. In the exam, you will be asked some very conceptual problems, okay, based on these topics that we have discussed. Okay, so thank you very much.